your computer is heating, and it's now generating more heat than real power. So if I want to give you a quantum course, we'll probably have until COVID's over, okay? So which means a couple of months, more than a couple of months. So I'm going to try to give you a glimpse of what quantum computing is, what it does, and why we need today that power, okay? So I will try to explain as seamlessly as possible and give you 3 use cases, basically, that are current, that solve problems who may not be, human-intensive problems, but then we'll see, how really quantum computing can help in the future. So let me start with a very simple, I would say, tale. Okay, I don't know if some of you play chess, but for some who play chess, you probably know how chess was invented. Okay, it was invented in India back in time, where a Maharaja was bored. Okay, he fought war, he won war, and then he was bored in his castle. And so he brought one of his advisors and says, well, advisor, try to find something to kill my boredom, because I'm just bored. And so his advisor went and thought for many nights, and went back with what would be the chessboard, and explained to Maharaja what chess was, and it was a figure of war and the mins, and the fact that you would kill the other king, and the Maharaja and himself played and played and played, and the Maharaja was really, really fond of the game and says, well, this is incredible. Thank you, thank you. What do you want as a gift, my advisor? I said, Sire, I'm a very humble guy. So if you can put just 1 grain of rice on the first square, then 2 on the second, then 4 on the third, 8 on the fourth, and so on, until the 64th square. And the Maharaja says, really? That's all that you want for inventing this beautiful game? Yeah, I'm a very humble guy. So the Maharaja asked his finance minister to organize the gift for his advisor. And the finance minister came back a few hours later, says, Sire, it's impossible. I said, what? It's just impossible. And you know why it's impossible? And you know how many grains of rice would be on that board if you just double the number of grains of rice for each and every square? You have an idea? Well, exactly that number. 18 billion, blah, 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 18 billion billions. Okay, I don't want even to read that number, it's too big. But it's 18 quintillion. So, which is 18 billion billion. So that's a lot of grain of rices. Actually, there is only 7 quintillion grains of sand on the Earth. So it's 3 times the number of grain of sands. And now if you compare that to the number of galaxies in the universe, there is only 2 million galaxies. So think about it. And the universe is pretty big. So it's just impossible. And why am I telling you that? Well, maybe because this is what we call exponential growth. And you may have heard of a law in computing science, which is the Moore's law. Okay, it was invented by, or discovered by Gordon Moore early in the 60s. Gordon Moore was the founder of Intel, the chip company. And so he discovered that basically the power of computers were doubling every 18 months on average. Okay, and so if you look at where we are, 2019, 2020, so basically we are far beyond where we were in the 60s. And now if you double that power in 2019, so you see that we go very, very far. So yes, we have a tremendous amount of computing power today. That's true in normal computers. But to solve some highly technical problems, this is not enough. And we are basically at the edge of what's possible today. And furthermore, we have really bigger issues when it comes to computer. Okay, I'm just figuring out that, Apollo 11, so, well, we got a problem. And the problem with current computer is the following. First of all, and you've experienced that, your computer is heating. And it's now generating more heat than real power. And actually there is another, and I'm not going to go into thermodynamics here, but there is an law that basically says that the more power you need, the more heat you generate, and at one point, you just crash, because it generates so much heat that you cannot process fast enough. And then there is the size. Basically, we are at nanomillimeters, so very, very, very small transistors today, and we cannot physically go further. Okay, IBM is currently burning the smallest possible chips on the planet as we speak, and so probably in the next 5 to 6 years, it will just be impossible to go further. Okay, and then of course it's not just fast enough. We cannot go faster. Okay, speed of light is the speed of light. And you know what goes faster than the speed of light? Well, eventually you will say nothing goes faster than the speed of light. Well, except that a small guy called Albert Einstein proved that, yes, speed of light cannot be beaten, but at the same time discovered and theorized a lot of fundamental laws. And I'm not going into all those laws because, again, it would be too long. But there is one of those which is called entanglement, for example, that says that two atoms separated by thousands of miles can behave exactly the same way at the same time. It's kind of very weird. So how do you have an atom somewhere, 1,000 miles away, that behave exactly at the same time, and so breaking the speed of light? Well, this is the beauty of quantum physics, okay, which does not behave like our normal world, if I say so. And so, and you heard on the video, so the guys were talking about qubits. And a qubit is basically a quantum bit. So we all know what a binary digit is. It's either a 0 or a 1. Well, the beauty with a qubit, and particularly with entanglement, is that, well, a qubit can be anything between a 0 and a 1 at the same time. Generally, I scratch my head for a long time, says, how can you be either something between a 0 and a 1 and be multiple of that at the same time? It's kind of completely impossible, and this is what, unfortunately, what quantum physics is about. And so what we have here is the representation, or physical representation in 3D of a qubit. So it is a value that is somewhere in space, okay, so on the circle, that has, and I'm going to the details, but that can have a state or a value between a 0 and a 1. And because it's not really a 0 or a 1, and it needs to be represented on that sphere, then it is what we call a complex number, okay? This is the beautiful I. And the complex number is basically represented through a matrix, or a two-digit matrix here. And so when you do that, and I'm not going further in the mathematics, that's the end of it, it basically multiplies not only the complexity of the system, but it multiplies the possibilities as well. And therefore, because of superposition and entanglement, we have created, or computer scientists have created, quantum computers. Quantum computer is not new. And you probably have in your pocket a smartphone, okay? And so I left on the table mine. But if you have a smartphone, probably you're a GPS in your smartphone today. Well, do you know that GPS would not exist without quantum physics, okay? The reality of the GPS today exists only because of quantum physics. The transistor exists because of quantum physics. The laser, the IRM, the solar panels as well. So this is the first quantum revolution as we know it, that has been existed now for the last 40, 50 years, okay? But then the second quantum revolution has come and goes through a couple of ideas. And I just want to give you four main big ones. The first is the cryptography. Cryptography allows basically to put some security on data. And by using quantum cryptography, you basically create unbreakable information. You cannot decipher it. And then, of course, because there is cryptography, there is telecommunications. You may not know, as we speak, that China has launched a couple of years back a set of satellites that use quantum telecommunications to send signals back and forth, okay, from a satellite. And so completely encrypted, undecipherable, and using entanglement and superpositions. So basically, you cannot, nobody can, even Donald, can intercept China's communication over the satellites. This is the first set of satellites, but probably we'll see more in the future. Elements of measures as well, so we can measure now very, very precisely a lot of things in physics thanks to quantum theory, and of course the last is quantum computing. So quantum computing allows calculation that are much, much faster. Now the problem is that this is a board, a computer board, like many of you have on your desktop, equivalent to, it's a laptop here, but the reality of about a quantum computer, it looks like that. Okay, you've seen it very, very briefly in the video. So it doesn't look like a normal computer. It doesn't cost, actually, the cost of a single laptop. It's a multi-million-dollar business. It's very fragile, and it operates at minus 274 degrees Celsius. So basically close to 0 Kelvin, which is quite cold. Okay, and of course, to get to that level of coldness, well, you need to consume a lot of energy. And it requires, and that's probably the worst part of it, it requires a new language. So you cannot program those computers the way that you're using, any normal computer language, C language or Java or any other like that. You need a complete different way of thinking and way of programming that computer. Now there are a couple of companies, very, very few companies in the world that have quantum computers, and I'm not going into the different types, but there are basically three more main types of computers. What you see that you find the big names, okay, the IBM, the Google, the Microsoft, the Amazons, Alibaba as well in China, Huawei as well in China, Fujitsu and NTT in Japan, Atos in France, D-Wave and others as well, who are American companies. So it's really a very, very close club of capable companies. Why? It's just because it costs a fortune, okay? Not only to build, but to operate. And it's still very, very early in I would say, the real usage of those computers. Now, what will it help to do? So we talked in the previous sessions about artificial intelligence and what it does. Well, it will go beyond artificial intelligence. So Jean-Simon briefly talked about neural networks. The problem of a neural network is the exact same problem that I was explaining with chess. It's an explosive combination. So as soon as you reach a certain level of depth in the neural networks, then it explodes. And the number of combinations cannot be processed by a computer, by a normal computer. So you need to go to quantum. So advanced AI, climate change, we're all faced with that. Viruses, okay, and health is a very, very key element in incurable diseases, particularly our cancer and other brain disease, for example. So we need to find cure, but normal research cannot do anything. So let me give you a couple of examples there. So the first one that use quantum computing, and again, it's early research, is in radiotherapy optimization. So basically, when you have a cancer, there is multiple ways to try to cure a cancer. Chemotherapy is one, and radiotherapy is another one. But radiotherapy is a big problem because it burns basically the tumor. But by burning the tumor, you burn as well good cells. So it's very, very difficult to calculate the exact power of the beam, the depth, and to just target the tumor section. So what a team in the US did is basically trying to use quantum computing, and I'm just building the slide quickly, to optimize the radiotherapy for cancer. And so basically modifying the beam intensity and to optimize the beam intensity to deliver the doses to tumors without damaging the nearby tissues, okay, that are healthy. So of course, there are a couple of obvious advantages. The first one is, well, we target better, so we cure the disease. But at the same time, it reduces the treatment time, okay? And the first test that it reduces the time by 1/3. So that means, less time in hospitals, less time in getting healthier. And so the idea is really to say, well, we can think differently and we can approach diseases in a different way. So, and of course, there are lots of challenges and insights. I'm not going to go into all the details. We'll circulate the slides and you will see that. But we're really in the field of the same, exponential growth and exponential explosion when it comes to calculation. It calculates 600 to 1,000 beams with different depth with different optimization issues. So very, very, big challenges there. Of course, it's very early stage, but the first results are very promising. A second one, which I was really stuck into a couple of hours ago, which is logistics optimization, traffic jams. Well, the good thing with COVID is that, well, there are less traffic jams, except when, you don't need one. But Volkswagen took an approach on that, and the same thing. When you think about trying to optimize the traffic of hundreds, if not thousands of cars at the same time, on a specific, even on a few number of routes, that becomes very, very complex. And they came up with, which is just here, that visualization is the heat map of a road between central Beijing and the airport. So of course, peak hours, you see that route, so everybody takes the same motorway, and it's red across the whole motorway, and that by just applying some quantum physics there, or quantum calculation, so they manage basically to see that we're less, less issues by using different routes, and how do we optimize routes in real time, because this is the basic behind that. And when you think about that is, well, in Beijing, so it's so they use a data set done by Microsoft actually of 10,000 taxis. And of course, you understand the challenges and the benefits here: optimized traffic, reduction of congestions. So of course, it's much better here. So it's really using quantum to solve real life problems that exist here. But I just want to share that thing, and yeah. So here, the first test that they did was on 418 cars on 3 routes. And when you apply that, there are 3 to the power of 418 possibilities. Okay, if you try to put that into your calculator, it will basically go away. Too many possibilities. So that's why basically a normal computer cannot process that amount of data. So, and of course we can add more things, the road capabilities, residential zones, and so on and so forth. So the more, I would say, constraint you had, the more difficult the problem to solve becomes. Last is in finance. So finance is very data intensive, very calculate intensive as well, calculation intensive. But there is a thing, and in the previous video as well, so Jean-Simon alluded on some aspects of AI. One of the things is, and I love this curve, is basically when you want to allocate assets, for example, among multiple asset classes, it's very easy from a calculation standpoint to find what we call suboptimal solutions. So, which is basically the bottom of the curve here. But to find the optimal solution requires, once again, a lot of calculations. So what they did, and what the company did in the US as well, is trying to mix the approach. So how we can go fast with machine learning, classical machine learning, and then added quantum computing. So the idea was basically to first find the optimal solution. So not the suboptimal, but the optimal solution, and get it faster. So meaning that you can have return on assets faster by reducing your risks when you allocate assets as well. So that's the whole idea. And I'm not going to go into more details here, but it's just to give you ideas of some of those aspects that can go through. Now I just want to put a warning there. There is a lot of quantum BS, okay? You will hear a lot about quantum, and people are putting quantum on everything these days, okay? So a couple of things. People said DNA is a set of quantum computers. Well, DNA and quantum computing is so far nothing related. Water memory, which is the homeopathy scientific explanation. I'm not going to say that homeopathy doesn't work, but water memory is not an explanation of quantum, or is not made by quantum. It's been proven multiple times. Quantum medicine, again, nothing in Deepak Chopra, very, very famous in the US, but he reads the book called The Quantum Body. Well, I don't know, he probably has atoms spinning in his brain faster, but there is no such a thing as quantum medicine so far. Quantum management, quantum marketing. China's released a big hoax, sorry for that, mostly on Instagram, about releasing a very, very, very incredible camera that allows you to see details miles away. They call that a quantum camera. Bullshit. And quantum refrigerator, who was released a couple of months back, saying, well, this is a refrigerator that consumes 0 energy. It brings the energy from the atoms around the refrigerator. Well, if that was true, man, we solve climate change immediately, okay? So this is another bullshit. But I love this one, okay? So this is, to me, the best, quantum BS. So quantum soft, it's just a name, okay? There's nothing quantum in toilet paper. Now, if you want to go next, and this is a very complex topic, there are a couple of books that have been written, to simplify the approach as well. So there are, those three are a good start. It's heavy lifting, but it's a good start to learn more, to understand how that works, and to see how we can go further. So just to conclude, it's a very young, technology, for sure. Applications are burgeoning. Don't believe hype, believe science, okay, and question science as well. There is a lot of hype around that. But as I said, very, very few actors on the planet. So if you hear from somebody that is not among the couple of companies that I've shown you who break through something, well, don't believe it, okay? It's just hype. Now, I will skip the video, last video. But I think that the one thing is get prepared. Just get prepared so that you're not surprised when it's really become mainstream.